Okay, we're going to continue on in section 4.3, and we're going to begin talking about the fundamental trig identities. The fundamental trig identities are basically defining the trig functions in terms of another trig function. And we've really talked about some of these already, the reciprocal properties especially. We've talked about those in the fact that the sine and the cosecant are reciprocals of each other. So the sine of theta is the same value as 1 divided by cosecant of theta. Okay? Or I could flip that around and say that the cosecant of theta is 1 over the sine of theta, which we've used when we were filling in our chart. Okay? Cosine of theta is a reciprocal of the secant, and tangent is a reciprocal of the cotangent. We also have these quotient identities, where the tangent of theta is the sine of theta divided by the cosine of theta. And that should make sense because remember what we talked about before was that the sine of theta really related to y and the cosine really related to x. And we had defined tangent initially to be the y value over the x value in our unit circle. Okay? And since the cotangent and the tangent are reciprocals, then that means that the cotangent of theta is cosine theta divided by sine theta. Okay? And then we also have these Pythagorean identities, which really kind of represent the Pythagorean theorem. Again, if you remembered that the sine is the y and the cosine is the x, our sine squared plus cosine squared could really be thought of in the same terms of x squared plus y squared, which was the equation of our unit circle. Okay? So these are all some different identities that we're going to use and apply in different problems. So these are things that you're going to need to work on remembering and knowing these formulas. So let's move on. Okay. Example 1, beta is an acute angle. The sine of beta is 0.6. We want to find the cosine of beta and the tangent of beta. Okay. Well, since we know that beta is an acute angle, what we can do is we can take this and we can come up with a triangle. And more specifically, we can come up with a right triangle. So here's our right triangle. Here's my angle beta. It's one of the acute angles. Okay? Now the sine of beta is 0.6. Another way we could think of 0.6, remember that's really 6/10. And if we think about our right triangle trigonometry from yesterday, the sine is the ratio of the opposite over the hypotenuse. So if this is my angle beta down here, then the opposite leg makes this leg 6. It makes the hypotenuse 10. And in order to find cosine and tangent, we need to know the remaining leg. Okay? So if we apply the Pythagorean theorem, we know that the remaining leg, and I'm just going to call it x, so x squared plus 6 squared is 10 squared. And if we solve that, we're going to come to find out that this remaining leg is 8. So the cosine of beta would now be the adjacent over the hypotenuse, which simplifies to 4/5. And the tangent of beta would be opposite over adjacent, and that's going to simplify to 3/4. So we can use this concept of trig and these right triangles to where if we know one trig value, we can draw a right triangle, fill in the appropriate sides of the triangle, and use Pythagorean theorem to find the other trig values. Okay. Number 2, we've got the cosecant of theta is 3, and the secant of theta is 3 square root of 2 divided by 4. Again, we could think about maybe drawing a triangle, or we could use the trig identities, whatever you feel is going to work best for you. We're asked to find the sine of theta. Well, we know that the sine of theta, sine is the reciprocal from the cosecant. So if the cosecant is 3, then I know the sine is 1/3. In part B, the cosine of theta, cosine is the reciprocal of the secant. So if I take the reciprocal of the secant, I have 4 divided by 3 square root of 2. Well, I don't want to leave that radical in the denominator, so we're going to multiply or rationalize by multiplying the numerator and denominator both by square root of 2. So that's 4 times the square root of 2. The square root of 2 times the square root of 2 is 2. times the 3 gives us 6. And if we simplify, we have 2 times the square root of 2 divided by 3. Okay? So, how are we going to find the tangent? Well, we're going to remember that the tangent is the ratio of the sine divided by the cosine. So if the sine of theta is 1/3, divided by the cosine of theta, which is 2 square root of 2 divided by 3, when I simplify, I'm going to end up with 1 divided by 2 square root of 2. And again, I'm going to have to rationalize. And I'll have square root of 2 divided by 4. So the tangent of theta is square root of 2 divided by 4. And notice again, we still don't know what theta is, but we know that all these relationships are referring back to the same angle. The secant of 90 minus theta, right? So there's another flash from the past from yesterday. Okay? We talked about complementary angles and their cofunctions. So if I'm talking about the secant of 90 minus theta, that's the same value as the cosecant of theta. And the cosecant of theta was defined as 3. So applying those trigonometric identities, those basic identities, to find these other values. Let's move on. Here what we're doing is we're verifying an equation. We're showing that an equation is true. And we're using those trig identities to do that. And we did some of this stuff with logs as well, where we wanted to verify an equation. So remember what we do is we're going to work with one side of the equation and leave the other side alone. We want to take one side and turn it into the other. So in the case of number 3, the more complicated side is the one with cosine theta times secant theta. And we want to show that that equals 1. And we're going to do the trig identities. We're going to use those identities in order to do that. So, cosine theta times secant theta. Well, another way to represent the secant of theta is 1 divided by cosine theta. And if I take the cosine of theta and I multiply by its reciprocal, remember when we multiply by reciprocals, it simply simplifies to 1. Okay? So we've used the basic trig identity and verified that the cosine of theta times the secant of theta is always going to be 1. Okay? So let's move on to number 4. In number 4, we've got a little bit different look. We've got secant theta, we've got tangent thetas. Okay, we're adding them in one term and subtracting them in the other. Now, you might be thinking, okay, secant, that's 1 over cosine. Tangent, that's sine over cosine. So I could put everything in terms of sines and cosines. Okay? But if we look at this, I've got the sum and the difference of the same two terms. So if I were to actually distribute and multiply those together, I'm going to end up with, secant squared theta minus tangent squared theta equals 1. Well, if we go back to our basic trig identities, one of the Pythagorean identities said that the secant squared was the same thing as 1 plus tangent squared. So, if I take secant squared theta minus, let's go another route. Secant squared is 1 plus tangent squared theta minus the tangent squared theta that's already there. And now my tangent squared subtract out, and I have 1 equal to 1. Okay? So using that substitution, that basic trig identity that the secant squared is the same thing, where it's equal to 1 plus tangent squared. And by making that substitution, we're able to verify, since 1 equals 1, that that initial equation is in fact a true statement. Right, number 5, we've got a fraction. Okay. The fraction would be the more complicated side. In order to add fractions, they have to have common denominators. So in this case, on the left side, the common denominator would be cosine theta times sine theta. So, what would I have to do to the first fraction in order to make its denominator cosine times sine? I would have to multiply numerator and denominator by a sine theta. Well, sine times sine would give me sine squared theta. In the second fraction, I'd have to multiply numerator and denominator by cosine, which gives me plus cosine squared theta. So now we should see that here is another of those Pythagorean trig identities. The sine squared plus the cosine squared is really 1. Cosine theta, sine theta. And now if I split this apart, I really have 1 over cosine theta times 1 over sine theta. Well, 1 over cosine theta is secant theta. 1 over sine theta is cosecant theta. So if I just rearrange my terms, I have cosecant theta times secant theta equals cosecant theta times secant theta. Okay? And we've reached our goal. We've made both sides exactly the same. Okay? So, number 6, incorporating these trig identities with the earlier topic of talking about degrees, minutes, and seconds. So I've got the secant of 5 degrees, 40 minutes, and 12 seconds. Well, what I need to remember is that secant is really 1 over, not sine, cosine. So I'm going to need to go to the calculator, and I'm going to find the cosine of 5 degrees, 40 minutes, and 12 seconds. So the first thing I'm going to need to do is I'm going to need to check my mode key, and I'm going to need to make sure that my mode is set to degrees. Okay? So I've changed my calculator to degrees, and now I can go back, and I'm going to take the cosine of 5 degrees, 40 minutes, and 12 seconds. So I got to go through all my menus here. Once I get that value, remember, I'm going to have to take the reciprocal. So remember, the reciprocal key is the one that has x would look like a -1 exponent. So if I hit that, I'm now going to take the reciprocal of my previous answer, and I'm going to round to 4 decimal places. I get 1.0049. Okay? So we found the cosine of 5 degrees, 40 minutes, and 12 seconds. And then we took the reciprocal. Remember, the reciprocal key is that x to the -1. And that will take the reciprocal of that answer that we got for cosine of 5 degrees, 40 minutes, and 12 seconds. All right, last problem. We're going to see how some of these things can be applied. We're going to look at page 276. I'm going to look at number 58. And in problem 58, it says that there is a 30-meter line used to tether a helium-filled balloon. So if we're tethering a helium-filled balloon, I can think of this as being the ground. Tether means that the line is being tied to the balloon, so the balloon is somewhere up here in the air, okay, wherever we want to throw it there. And then we would measure the distance from the balloon to the ground using the perpendicular, using the altitude. And it tells us that that line is 30 meters. So here's the line that's tethering to the balloon. That's 30 meters long. And it says because of the wind, the line makes an angle of approximately 75 degrees with the ground. So that's going to be this angle right down here. Okay. And ultimately what we want to find is the height of the balloon. Okay. So here's my h. I'm looking for the height. And this turns into a very simple right triangle trig problem. Okay. From the 75-degree angle, I'm looking for the opposite leg, and I know the hypotenuse. Well, if we remember from yesterday, opposite over hypotenuse is the sine. So we will take the sine of 75 degrees, and that would be the ratio of the opposite leg over the hypotenuse. So how do we solve for h? We got to get h by itself, so we're going to multiply both sides by 30. So I have 30 times the sine of 75 degrees equals h. So again, my angle's in degrees, so I need to make sure that my mode of my calculator is still in degrees. And I'm simply going to type in 30 sine of 75, enter. Okay? And I get 28.9777, so we're just going to go ahead and say that that height is approximately 29 meters. There is a simple application using the trig and the right triangle trig to allow us to find a height that we can't really measure directly. So that's going to conclude today's lesson. So you need to make sure that you've got those trig identities down, and you need to make sure you start working on remembering those identities, some of them that we talked about. You've got the reciprocals that we talked about before. And then those Pythagorean identities really come in handy when we're doing some of the verifying the equations or showing that an equation is true. So, we will see you tomorrow, and we will do some more work with trigonometry.